All right, Charity, do you think we should get going just with intros?
Oh, perfect. Yeah. Sorry, I think I was frozen. Yes, please. Kelsey, take it away. GRASP members, thank you for joining.
Okay. Hey, guys. Nice to virtually meet all of your Zoom icons. It's great to see you. I have the pleasure of being joined by 3 of our engineers here at Zoox. So just a quick heads up for what we're going to do over the next hour. I'll have them introduce themselves. We'll do a very quick, I'll try to keep it brief, high-level overview of what Zoox is doing, and then I will toss it to Sarah, Kai, and Marin to go further into their focus areas. So to start off, my name's Kelsey. I've been at Zoox for a little over 4 years, and I run the University Relations program. And yeah, that's pretty much what brings me here. So anything about internships or questions about that, I am happy to help. And then we'll go Kai, Sarah, Marin for intros. So Kai, you're up.
Sure. Hey, everyone. My name is Kai. I've been at Zoox. In February, it'll be 5 years, so it's quite some time. And I lead the prediction team at Zoox, and I'll be talking more about that in the presentation.
Kelsey, I've already forgotten who was supposed to go next.
You can just say your name and what you do. I think that's a good start.
Yeah. Awesome. So hi, everyone. Thanks for being here. My name is Sarah, and I lead the prescription team here at Zoox. I've been here almost 6 years.
Hey, everyone. My name is Marin Kubilarov. So I've been at Zoox 5 years, 3-4 months, something like that. My role, I give technical guidance to our planning and control group, and I also more specifically focus on our research efforts within planning and control. And I'm also a professor at Johns Hopkins in mechanical engineering and computer science.
Cool. Awesome. Well, I will jump right in and share my screen. You guys, I think if you're able to submit questions via the chat, you can do that. Otherwise, we have left time for Q&A at the end. So if I'm able to stay on time, which hopefully I am, then we can cover any follow-up questions then as well. So can you guys all see my screen okay? Yeah. So obviously, thank you for coming. This is about Zoox. What Zoox is doing is we are creating autonomous mobility from the ground up, which is a very nicely packaged statement, but it's actually pretty hard when it comes to executing it. The reason that we're doing this is because the model of individually owned human-driven vehicles is broken. So those are the cars that we drive today, the Ubers that we're getting in, pretty much all the cars that you see on the road. There's a number of reasons why this is not the ideal way to do things, none of which should be a major surprise to anybody. Obviously, they're very dangerous. 1.4 million people lose their lives every year just because of car accidents. So when you're stuck in traffic and there's an accident and you're kind of just annoyed because you're going to be late to work, that's actually somebody's life that could have been taken. So that is a huge thing and something I think a lot of drivers just come to accept, but you probably shouldn't. So lots of work to do on the safety side of things. Idle assets, unless you're using your car for your profession, driving an Uber, doing DoorDash, delivery, stuff like that, you're really only using your vehicle about 4% of the time. So the other 96% just kind of sitting there, depreciating in value. I'll add that too. Congestion. So if you have driven in the city, I'm from Philly, so I know Philly traffic is not ideal in the city or around it, but no cities have really figured that out. So you can assume that 1 out of every 3 people in cities is looking for parking at any given time. So that means that 1 out of every 3 people are also just sort of driving around circles waiting to see a spot that will maybe fit their car. Exhaust, climate change is super real. So, vehicle exhaust is not all of it, but it's a big chunk of it. So we can definitely do a lot to reduce that. And then this last number, I always think it's kind of funky. I don't know where they came up with 400 billion hours, but I think the point is that we could be using our time doing something a little better. I think it's more rare for people to buy cars for the pleasure of driving. We're usually buying them out of necessity. So if we could utilize our time in transit a little better, I think that that would be more effective. So we are approaching this challenge by transforming mobility as a service. So not individual ownership, we are offering you this service by developing a fully autonomous purpose-built vehicle fleet that's designed for AI to drive and for humans to enjoy. So you'll sort of see that theme throughout this presentation. To start, I'll start with mobility as a service. So the actual product that we'll be offering, this is a picture of our vehicle. It's not a rendering. It does drive in both directions up to 70 miles an hour, and it's super cool. I think from a sort of high level overview, before we get too technical, if you're just looking at it from a rider standpoint, it's much more rider friendly. There's carriage seating, spacious interior, sliding doors, and all riders are given the same type of comfort. So there's no sort of bad seat. Nobody's, you don't have to like call shotgun or anything like that. So everybody has the same good seat. Everybody has the same safety, and it can definitely be customized. And then you compare that to the vehicles that we drive today, and it's always like getting in the back of someone's Prius is just less exciting. So we have to build this vehicle. We can't just sort of magically dream something up. And that's sort of where the vehicle engineering and advanced hardware engineering side of Zoox come in. So obviously software is a huge part of that, but if we're going to have this purpose-built platform, we have our vehicle. So just the three sort of main areas I want to touch on: the powertrain, the safety, and the manufacturability. So our powertrain, again, think that this is intentional. Everything about the Zoox vehicle is intentional. Our battery is built to last up to a full day of ride sharing, which means that we don't have to stop every 6 hours to recharge, which means that we're getting more business. Redundancy and safety. So I mentioned before, every passenger has the same sort of safety standard applied to them. So in most vehicles, the crash test rating is only for the front 2 passengers. So all 4 are considered equal here. And then of course, we're able to add in additional fail operational designs where if something happens to the vehicle in the middle of somebody's ride, it will still be able to execute and finish the ride, and then address whatever it needs to. And then manufacturability. So I had this little video playing earlier. All of these are clips from much longer videos that are online if you're ever bored and want to go see that. But we work with a bunch of great suppliers overseas and in the US, and they make it so that our assembly lines can be very reduced, and it's sort of just to really dumb it down, putting together Lego parts by the time that it gets to our manufacturing site. So it does make it very easy. Maneuverability, so there's 4-wheel steering, there's bidirectionality, it's completely symmetrical, and that has vantage points all around. So both from where we can place our sensors, how far we can see, navigating in tight spaces, and just overall making for a smoother ride. And then serviceability and durability, back to being intentionally built. This vehicle was not built to be used 4% of the time. This vehicle was built to really, really be used pretty much 100% of the time, except for when it's being charged. So we're looking at a useful lifespan of greater than 400,000 miles. And that is useful. So everybody has that one car or knows somebody who has that car where it still works, but it's not really something you'd rely on. So this is something that's really important to us. And then we go into software. I'll just say that the manufacturability, hardware, vehicle side of things, there's a lot more to dig into there. So if that is something you're interested in, please go look online. We have a ton of information, but this session is mostly for software. So I want to make sure we dedicate the right time to that. Let's see, teleguidance is one area of our software stack. It basically allows us to navigate around edge cases. So because this vehicle is not operating at level 5 autonomy yet, there are still going to be times where we need the human eye to take over. So you can see in this video that a new path is being formed, and that's being done by a human operator. And what it's doing is it's not driving it, using a remote control and driving it remotely from hundreds of miles away. It's giving the vehicle new permissions, letting the vehicle decide and still technically drive and execute that path autonomously. We're only doing this for less than 1% of sort of our complex areas, but obviously our AI is going to be learning as we do this more often. And we test primarily in San Francisco and Las Vegas, which there is no shortage of complex infrastructure, layout, population, two very interesting cities to learn how to drive in. Simulation allows us to test and validate our vehicle software before it goes on our vehicles. So again, looking at these edge cases that we may not see every single day, but we still need to know how to handle them, we can create a simulated environment and execute them and still have a lot of learnings taken out of this area. And then, so the last three, and these are the three that we're going to dive into a little more with Sarah, Kai, and Marin, but mapping and localization. So this is how the vehicle knows where it is in the world. And if you've seen any of our driving videos, you know that the streets of SF can get very narrow, especially when nobody knows how to parallel park. So we can't really afford to be off by an inch or two. We need to know to a centimeter level where we are in the world so we're not running into things. Perception is what the vehicle is looking at, to put it very high level. So we use a combination of LiDAR cameras and radars. Our vehicle will be able to look at things, track them, classify them, all in real time. So it's obviously important to know, like, that's a truck, it's probably going to move. That's a tree, it's probably not going to move. And then planning and prediction. So we know where we are, we know what we're looking at. How are we going to execute what happens next, and how do we make sure it's the best way to do that? So that's using everything from our prediction and planning stack, especially with things like dense crowds, pedestrians, complicated traffic environments. This is really important to sort of know all of the different paths that our vehicle could take. So I ran through that, but you guys didn't come here to hear me talk. So I will hand this over to Sarah now, and Sarah, just cue me whenever you want to switch slides.
Sounds great. Thanks, Kelsey. Like I said, thank you everyone for coming to this session. Let me start off by talking about perception. So perception is the eyes and ears of the driving stack. It really enables our vehicle to reason about the world around us and provides downstream stack that includes prediction and planning with all the information they need about our surroundings in order to be able to drive safely and comfortably through these. There's a variety of sensors that you can use to achieve this goal. For example, people use just cameras, other people use other things. At Zoox, one of our core tenets is safety through redundancy. So each available sensor has its own pros and cons, and we've chosen a set that allows us to cover a lot of these important axes. So I'm going to talk a little bit about our three primary sensors: camera, radar, LiDAR. We do have like some more things like audio perception, which I don't talk about. And here's a matrix just sort of like showing why it is that each one of them is important. So cameras, for example, they have very high resolution that allows us to see small important things off in the distance. They also have color detection. So they're really the only sensor that can see traffic lights or vehicle lights. They're pretty low cost. In comparison, LiDAR is more expensive, but it has really great depth perception. You can use it for a lot of tasks. In addition to perception, for example, localization. It also isn't affected by adverse lighting conditions like night, which camera is. And then we have radar. Great at night. It not only senses depth, it also senses velocity. And it's also really great at adverse weather conditions. So for example, if you've got really heavy fog, really heavy rain, radar doesn't have an issue with that. Camera and LiDAR do get degraded. So our stack is built on all of these sensors. I'm not going to be talking a lot about some of these, and that's partly in the interest of time and partly because vision is a sensor, sorry, vision is a modality that a lot of people are familiar with. So in the perception side, I talk a lot about vision, but of course, our stack is treating each of these modalities equally. So we have radar processing, LiDAR processing. We also have tracking and fusion, just things that we are doing, combining all of these sensors that we don't talk about here. Okay, next slide, please, Kelsey. Okay, so let me give a very quick introduction to our vision pipeline. So there are cameras that are mounted all around the vehicle. Same for all of our other sensors, by the way. We have 270-degree coverage all around the vehicle. So these cameras are streaming video to our compute systems. for every frame that we are deciding to process, we are doing a lot of different processing on it. So that starts off by a main detector that is multitask. So input images, output comes 2D boxes, 3D boxes, semantic segmentation, instance segmentation, really a lot of sort of core building blocks of vision. Next up, we're tracking each of these dynamic entities over time. And then we are computing attributes on them, which can be multi-frame attributes. For example, vehicle lights really requires a track over time, or they can be single frame attributes. So I'll go a little bit more into detail. Next slide, please. So like I said, the very first thing that we're doing is a multitask network that is outputting a lot of sort of key information from vision. So here's some of the images. And this was actually presented in a paper that we covered this year in WACV. So we have instance segmentation, semantic segmentation. Instance segmentation is just like for every pixel belonging to a certain instance of an object, we identify it separately. Semantic segmentation, what is for every pixel the class of an object? Is it a car? Is it a bus? So forth. We are also from one image producing a depth map. So for every pixel, what is its depth in the scene? And then you can see this projected into a pseudo LiDAR point cloud. And then there's many different classes that we're detecting here. There's normal classes that you would expect, cars, buses, so forth. Because we are also operating in San Francisco, there's a couple of interesting classes here. For example, trams, pedicabs. We also encounter a lot of dogs, so we've got animals there as well, so on. Next slide. Next slide, Kelsey. Oh, cool. So here's a video that is showing some of this output. We can just take a look at this. Let's play that video. So let's start off by the 2D boxes. So we have like traffic lights, classification for traffic lights. I don't know if anybody saw that dog there. We also have instance segmentation. So every pixel colored by the instance. Every car is unique there. The classification, semantic segmentation. Here we've collapsed many of the classes together for ease of viewing, but we compute many more classes like vegetation and so forth. This is the depth map that we're computing for every pixel. What is its depth in the scene? And then another higher level signal that we have on top of that is regressing 3D boxes. So from one image, being able to say what are the 3D boxes of all of these objects. For example, here we were showing vehicles. Next slide, please. So something that is important to remember when we're doing self-driving is not just dealing with the ordinary cases, but really sort of remembering that there's a whole long tail that you have to worry about. So the detectors and classifiers that we built, we try to be very robust to these long tails. For example, you can see pedestrians and bicyclists in the world normally, and you can see them standing up maybe or walking. You might not see them in weird positions. So for example, crouching or bending into their car. You might not see them in weird lighting conditions. So for example, here sort of like illuminated by just headlamps. And in some cases, the entire class might look very different because of its appearance, like these bicyclists. And we sort of have to engineer both our data and our networks and the losses to explicitly deal with this. Next slide. So in addition to this core detection, semantic segmentation, and instance segmentation, we also have a number of attributes that we're computing, like I mentioned before. I'll go over two of the classes and some of the attributes, pedestrians and then vehicles. So first up, we have skeleton detection. Let's play the video. So for each pedestrian, we detect all of the key points on their skeletons, like their hands, their elbows, their torsos, and so forth. Actually, this looks like construction workers. Kelsey, did we skip a video before? Yeah. Can we play that one? Awesome. Yeah. So for each pedestrian, there's a number of key skeleton points that we're detecting: their hands, elbows, torsos, knees, and so forth. And in this video, we are showing some of these skeletons detected for some of the people that we encountered in our drives. And then we can use these skeletons for computing other higher level tasks on top, for example, tracking and gestures and so forth. Another thing that is really important to detect in people is, are they standing or walking? And this is something people can tell by just looking at a single image. And it's very important because the difference between somebody standing and all of a sudden walking can be milliseconds. So in our stack, we have a network that is classifying, given a couple of images, whether a person is, their stance is a walking stance or a standing stance. Okay, next slide. And then the video that we had showed before, construction workers. So semantics of scene are very important. Understanding that people are construction workers is important because a construction worker in your path might require that you have to slow down or stop or understand somehow that the rules of the road have changed. So let's play this video. What we're gonna see here is a number of construction workers that are off to the right of us. And you'll see we are classifying them as construction workers because there's a little very hard to see icon of a hard hat. And understanding their construction workers along with sort of understanding the semantics of the cones and so forth helps us understand what our paths should be. In addition to classifying somebody as a construction worker, we also classify whether they're holding the sign or not. So towards the very end of that video, I know it was very short, we were classifying, perhaps Kelsey, we can play it one more time. We were classifying whether the person was holding the sign up. We also do it sideways because that makes a difference, right? Like if you're holding it sideways, probably means it's not an enforced sign. So let's just wait until the second video shows up. Okay, so here you'll see the person who's holding a sign. We've got a little icon on top that shows that he's holding a sign up. Next, please. Another signal that we use as humans to predict what people might do in the future and how we have to behave around them is how distracted they are. So let's play that video. And generally, an alert driver will try to be more cautious around people who are distracted. So here you'll see anytime somebody's using their phone, we have a little phone icon next to it, like this guy over here. I think he was looking at it and taking a picture. And one of the funny things that we found is there's a lot of attributes that we are annotating and classifying for people. I think we have probably 30 of them. And being on your phone is one of the attributes that we most commonly identify. So it's sort of like, you know, people are not doing much else besides walking and standing and being on their phones. Next slide. The final signal that we're going to cover for pedestrians is incredibly powerful, and it's pedestrian gestures. We found that gestures correlate very strongly with what people are going to do in the future. So let's play that video. And here's a couple of examples where we detect when people are indicating that they want us to stop by holding up their hands. So this guy is going to be, he'll stop, then he'll hold up his hand, then he'll cross because that was his plan. And then the opposite, which is they're waving us on. So police officers will usually do that. Okay, let's move on. So let's switch now and talk a bit about vehicle attributes. There's several important attributes we compute for vehicles. For example, classifying vehicle lights. Let's play that video. So vehicle lights such as indicator lights, reverse lights, and brakes and hazards are very important indicators of the intentions of the drivers around us and are one of the signals that Kai will then use in his models for prediction. In addition to these normal vehicle lights, we also have emergency vehicle lights. So on the next slide, we show some of these. So emergency vehicles are important to classify. And on top of that, you have to understand whether their lights are on or not. The presence of both of these can tell us something about what it is that we need to be doing. So if there is an emergency vehicle with its lights on, that usually means we have to alter our path or slow down or stop, pull over to the side of the road. We probably have one more emergency vehicle video here. So yeah, you can see by that icon on the top with the little flashing lights that we're detecting these lights. And in addition, we also have microphones mounted on our vehicle, so we can also listen to and identify the sound of vehicles that emergency vehicles make. Okay, and then the final attribute is open doors. I actually don't know how we're doing on time, so we could just skip this and move on. But basically, open doors are another very important attribute that we use for figuring out whether we need to stop or swerve in order to not hit like something that opens all of a sudden in our path. Okay, so next up, let's talk about LiDAR. For those who are unfamiliar with it, LiDAR is a three-dimensional sensor that measures distance to objects via reflected laser pulses. So here's an image of a scene where we are showing all of the LiDAR point clouds detected by all of our LiDARs. If you've seen our vehicle, we actually have sensors mounted on the corners of the vehicle. So this is the same for LiDAR, and they're color-coded. The points here are color-coded by the ID of the LiDAR. So between all of our LiDARs, we have great coverage all around the vehicle. Next slide, please. We extract several features from our raw LiDAR data that we then use for higher level tasks like instance segmentation and classification. One important feature is LL3D, our local life 3D map. So we start by voxelizing our LiDAR data into voxels. We can then fit local surfaces or surfels to each of these voxels. And aggregating this data over time, we can create a rich geometric view of the world. In addition, we can raycast through this to understand which voxels are occupied and which ones are free, which ones are occluded. And this information is very useful for other parts of our stack. And finally, all of this is implemented on the GPU so that it's in real time. Next slide. Like I said, we are doing these higher level reasoning. So for example, semantic segmentation. And we're doing this on a per point basis. Here's just the same scene now colored with our semantic classes that we're detecting, and the key is on the left. And this, this network is actually bootstrapped by using our vision-based semantic segmentation network. Next slide, and then we can segment all of our objects into their sort of instances. Here we're showing all of our dynamic objects. This is an interesting scene. It's actually a lot of motorbikes that were passing us on the left. So all those orange blobs are motorbikes. The blue ones are cars, red ones are pedestrians. And then finally, let's go to the slide after. Now we have a video that's showing LiDAR only detection for that scene. Awesome. So like I said, this is a very incomplete view of our system. I've skipped entire modalities and lots of other processing, but hope that gives you an idea of some of the work that we're doing. And I'll hand it over to Kai.
All right, thank you, Sarah. Cool, so I'll be talking about prediction in this section. So basically prediction operates on all of the things that perception provides us. Including all the locations of the dynamic entities around us, all the cars, pedestrians, bikes, their current velocity as estimated by perception, and other attributes like what Sarah was saying, like standing, walk, run, vision attributes, LiDAR attributes, and things like that. And so those are all things that we consume to try to make a prediction about the future of what these agents are doing. So this is just showing a visualization of what we think is like the single most likely future for each one of these agents around us. And like, I think, you know, prediction, I think as a topic area is probably less well kind of known about versus like something like perception, which has a much longer history and like computer vision and things like that. But, you know, I think what I think is interesting about prediction is that driving around dynamic agents is kind of one of the reasons why AV is hard. And the big part of driving around them is to be able to kind of, you know, infer what they're going to do in the future in order to like for us to eventually, you know, do some safe paths. And so, you know, that's the task of prediction. That's why I think it's pretty interesting. It's also kind of nice in that the way we frame the problem, you kind of have unlimited training data because, you know, when you have a log, you can just see where everything ended up in the future in that log, and that's kind of your training target. So prediction is really amenable to like some like data-driven techniques like machine learning and things like that. And also, I think I'd just like to add that, like, you know, my background before Zoox was not prediction. It was in computer vision, machine learning. But prediction as an application area is definitely one of those tasks that someone can pick up if they have an ML background and are kind of willing to learn the nuances of this problem. And finally, I think, you know, predictions like as a technical problem is relatively young, and I think there's a lot of opportunity for new ideas and techniques. So that's just kind of for people who aren't aware of what prediction is, that's a little bit of an intro. Next slide, please. So yeah, I wanted to give you kind of a flavor of what things we output in prediction. So overall, we try to infer both the intents and high level kind of attributes about what agents are doing. And one example of this is at the top row shows we're recognizing that these are double parked vehicles. So they're kind of like going to be stationary for like long-term stationary vehicles. And drivers in cities, you know, this is a very common occurrence. You know, there's like a ride share or a truck, delivery truck or something like that, and they're kind of parked there. But, you know, as a human, you'd want to navigate around this thing. And so to do that, we have to recognize that they're in that state. So that's one of the tasks that is worked on by prediction. Another is kind of, you know, another type of intention is like when a pedestrian is near a sidewalk. As a human driver, you would kind of know is this pedestrian intending to use this crosswalk, or are they going to stay there so we can pass them by? And so this is another one of these tasks that we try to recognize in prediction, and they all kind of relate to like what the future state is of these agents. Next slide. Another thing that we do in prediction, in addition to kind of understanding these high-level intentions of agents, is to actually model the specific future trajectory of these agents, kind of from where they are at the time of perception up to around 8 seconds into the future over a long time horizon. And like that's another critical thing that you need to do in order to safely navigate around these dynamic agents. And what you'll see here is that the car is kind of pulling out of the parking space, but it takes it a little bit wide. And so as a human driver, you'd probably recognize this and slow down. And then what we're showing is we can kind of capture similar behavior here, or we see that where we basically predict that their future trajectory is going to come into our lane a little bit, and then therefore we kind of like nudge and slow down to account for that. So trajectory regression is one of the main tasks in prediction as well. Next slide. So yeah, to give you a flavor of like how do we approach building algorithms for prediction. There's kind of numerous ways you can do it. Naively, you can just say like, you can just take whatever the velocity is of an agent and just say like they're just going to keep going with their velocity, and maybe like some other motion model for that. But those things I think end up kind of breaking down a lot, because you have to take into account kind of the full scene to really do prediction well. You need to be able to take into account what is the road geometry, because that's a very strong prior to what agents are actually doing. In addition to like, what are the other attributes that we know about this agent? How is this agent related to other agents? What's their kind of configuration relative to each other? And so all these things you really need to kind of take into account to actually do like to build like a nice prediction system. And so the way that we kind of approach it is, we try to build a representation for our machine learning models that does spatially try to capture everything around us into kind of like the same kind of the same space, the same geometric space. And so what you see here is that what we'll do is we'll kind of render everything into this we call a top-down representation, just all around our vehicle, so that everything is kind of co-located with like things like the Z-line, which is kind of like, which other people call like a HD map, just like the road geometry, but also kind of the location of everything. And so that way, when we give it to our ConvNets, it gives them kind of at least the ability to see where everything is related to everything else. And that's kind of the basis of like how we formulate the input for our prediction systems. And, I think like this is kind of like the vanilla way that we formulate it, but there's like this as an area of like, understanding what the right representation is kind of still like a really active area. And you know, I think there's potential for new ideas there as well. Next slide. So yeah, so on the topic of prediction trajectories, like I said before, one type of trajectory that is, you know, when you're driving in a city is, you know, people will follow the road. So if you look at the image on the left, the pink trajectories show, you know, these are strong priors that our map provides us of, you know, is a car potentially will stay in their lane, will take a right through the junction, do a lane change, things like that. So those are kind of one class of trajectories that we represent. Another class of trajectories that we represent are when cars don't follow the road geometry, and that's quite common as well. So for example, if a car is pulling out of a driveway or making a U-turn, you know, we still want to give them realistic trajectories. So what you'll see here in the video is that the car pulls out in front of us and we give them trajectory, and then another car does the U-turn, and we can still give them like a so-called free-form trajectory. And I think that really kind of shows the power of the top-down convolutional method. So, you know, I think that just shows the capabilities. I think that's my dog barking in the background, but yeah, so this is just on the topic of trajectories. Next. And finally, I think, you know, one thing to keep in mind is like, for whatever algorithms are developed for dense urban driving, they need to be able to scale well with really crowded scenes. So like here, what you see is there's a lot of pedestrians around us, and you know, something that scales poorly is, you know, is not going to be acceptable. And so the nice thing about these convolutional methods is that, you know, they do not, there's kind of like a one shot for the full scene, and then you're kind of done. So those are nice properties that we try to have. All right, next scene. Okay, and I think I'll hand it off to Marin. So thanks, everyone.
All right, and I think I'm going to let Marin share his screen so he can control his videos.
Great, can you see that okay?
Yep.
Yep. Okay, great. So in addition to perception and prediction, the third key area in our autonomous driving stack includes decision-making, planning, and control. And oftentimes we kind of collectively refers to that component as the planner. The planner is responsible first for safely driving the vehicle, then for completing the mission, and third, for doing so in a comfortable fashion. And so, kind of as an overview, at a high level, the way the planner works is by encoding these three notions of safety, progress towards the mission, and also comfort as some type of performance metrics, and also as a set of constraints. And then choosing one among a number of possible actions, control actions, to achieve good performance while satisfying these constraints. And so what I'm going to do is try to illustrate these concepts a little bit better with a few examples. And maybe we can start with this one. All right, here we go. So the most important type of constraints are those that encode collisions with other traffic participants like pedestrians and vehicles. And obviously those are safety critical, hard constraints that must be met at all times. And then we have constraints related to rules of the road, like this red light here, that in nominal conditions also must be satisfied as hard constraints. Now, the way the planner works is using a map as a prior, which also encodes the route or the mission of the vehicle. But we also must be able to process real-time perception and prediction, be able to adapt to any unforeseen changes in the map, such as, for instance, this construction zone. And in some cases, we need to violate the rules of the road, like, for instance, entering the opposite lane in order to navigate these situations. And in addition, we also must be aware of how to safely negotiate in these more complicated situations like here, where there's very little room to proceed. And in addition, our perception is obstructed. So we need to be extra careful and really slow down in order to avoid any collisions, which might not be obvious based on current perception, but could potentially occur once we are past that occlusion. And so in addition to this, the planner must also be able to drive the vehicle in different situations, both in the city, but also in the highway, like here, and have a sufficiently long planning horizon so that, for instance, here knows when to change a lane in order to be able to exit the highway on time. Another example here, and actually this would come up in several cases as a recurrent theme, very important to be able to react to conditions and to other agents that are not following in the rules of the road, like these vehicles that are kind of double parked in random locations, and be able to relate, again, our ability to predict how the environment might change in the future and be extra careful when handling these situations. And so this was a case when we were driving at night. Similarly, the ability to handle different road conditions like rain, in which case we typically use a lower velocity for extra safety and still be able to handle the various conditions. Another interesting case here that illustrates the need to, in many cases, to be able to assert our intent and also to capture the fact that other agents in the future can interact with us. That's especially important in these kind of dense traffic situations where the only way for us to make forward progress is to be able to kind of assertively merge. And then the planner figures out that to optimize our forward progress, we need to make several more lane changes. All right. And then we'll look at a few additional examples. Just increase the resolution. Doesn't work. All right. So another case here of going around multiple agents. And then here dealing with agents that might not be going in the right direction. And really important to not make any assumptions, again, about following rules of the road. Cases where we have a combinations of both, it seems to come back. Yeah, so what we'll see in a second is a case where we see a combination of a stationary agent, but also a number of dynamic agents, and important to be able to, yeah, like right here, to be able to handle these combinations. So one, all right. All right, I apologize for that. Let's see if I can come back and finish this. All right, here we go. Yeah, and this is now another very interesting example. Okay, my mouse doesn't seem to work great. All right. Okay, so that's a very interesting situation. And if you pay close attention, you will see a pedestrian that will jump out in front of us right here. And actually this situation, even for a normal driver, it's very difficult. And here we're able to stop sufficiently on time. Again, super important not to assume that other agents are following rules of the road and be able to account for edge cases like this. Similarly here, where other vehicles are kind of doing very drastic maneuvers. And a few more examples, again, with some edge case maneuvering and some handling of obstructed scenes. Okay, so I think I will move on. I wanted to mention also briefly, Kelsey showed in the beginning our new vehicle that was revealed in December. In addition to obviously being very careful about the design, one important aspects of building such a fully autonomous vehicle is to have very, very precise control, in the sense of once the planner produces a trajectory, the ability to follow that trajectory with very high accuracy. And these are just some videos, actually early videos illustrating control of an early prototype of that vehicle. And what it's showing is actually a comparison of a two-wheel steering mode, where we're going to try to execute a kind of a very aggressive lane change maneuver at 48 miles an hour. Not a typical lane change, but something kind of to test the dynamic maneuverability of the vehicle. And then this is the same maneuver, actually exact same conditions, but with four-wheel steering enabled, which is one of the features of the new Zoox vehicle. And so what we observe basically is the exact same maneuver, but executed much more smoothly and with less effort. And essentially what's happening here is with four-wheel steering, what you can do is execute the same maneuver with only a fraction of the steering wheel angle, particularly between 50 and 60%, which drastically increases the efficiency and also stability of the vehicle. So I think I'll stop here and just mention a few open questions. Again, this was just a very kind of high-level overview, hopefully gave you an idea of some of the challenges that we're facing, and some kind of more specific open questions that we are working on at the moment, the research challenges. One is, how do we build an architecture that combines both model-based and machine-learned components? And by model-based, I mean, these are human-coded models that are based on kind of known physics and logic that's well understood, but also supplemented with machine learning components and with provable guarantees. Then the second one would be, and again, we mentioned this several times, how do we safely handle and adapt in an automated way to unseen edge cases in a safe manner? And a third very important area related to be able to validate the vehicle is, how do we achieve very high fidelity simulation so that we can perform and drive many millions of miles in simulation for validation, also reinforcement learning. So I think I'll stop here so we have some time for QA, and I will stop sharing. Thanks, I apologize for the video mix-up. Here we go.
All right, so you guys, we have about 7 minutes left if we have a hard stop at 6 ET or 6 p.m. your time. But yeah, I'll open up the floor. If you guys have any questions, just unmute yourself and yeah, go for it.
Do you have an open world object detection pipeline? Because I know one of the things you talked about was for objects, you know what they are, you have attribute detection. But do you have a system to recognize objects that you don't know what they are?
Yeah, that's a good question. So there's a couple of answers. One, even within vision, yes, we sort of classify objects that we understand, and then we classify objects as it's a dynamic thing. I don't know what it is. And now you sort of have like some degradation, right? Like maybe you don't understand all of its attributes, but you understand it's a thing. These are its bounds. And that's not just true in vision side, it's also true in like our other modalities. So LiDAR is supposed to do the same thing, right? Like these are things that I understand, and this is like sort of like a static thing, and this is a coherent dynamic thing that's moving.
How do you, sorry, how do you just determine that human intervention is needed? And under what circumstances does this happen?
Yeah, so there are certain situations that we currently consider out of our operating domain. For instance, this would be a case where there's a very difficult construction zone with somebody directing a traffic, which is not obvious for us how to proceed. And in those cases, it's necessary to invoke teleop. And yeah, so that would be a typical case. Or for instance, if there's some police activity that we also consider out of our operating domain.
So these are like hard rules.
Yes.
Okay, thanks.
And the thing that I wanted to add is the operating domain is something that can evolve over time. So right now we've said there are certain construction zones we can handle perfectly well. We've been doing them for a while. Other ones that are difficult enough that we call teleop. Over time, as the capability of the system gets better and you can really validate that's able to do more and more maneuvers, the system can decide it can do some certain things and it doesn't need to stop and call teleop. So yeah, NOTD is something that we define.
Hi, thank you for the talk. It's very informative. I have a question for Kai. Would you be able to share with us what made you decide to change from computer vision to prediction, and how did you make that change?
Well, computer vision was solved. So what was it? No, I'm just joking. I mean, part of it was like, I mean, practically speaking, there was a need within the company that like we had to build up a prediction system. And so like, I think there was early on that was recognized that there was this need that was maybe not as obvious at the early times in the company. And so I think that that kind of was the basis for it. But I think, my interests being in just like more machine learning, it kind of fits really well with that. And so I think I would actually encourage, anyone who is generally interested in machine learning and maybe wants, to something a little different from kind of, other kind of well-studied problems. I think prediction is actually a very interesting field. So yeah, I would say part need of like, based on where we were as a company, and it just, I think the topic just matched well with kind of my interests.
Thank you.
Hi, I just wanted to kind of understand, does the Zoox vehicle kind of communicate with its outside world, maybe with other pedestrians or drivers?
Marin, do you want to take a stab?
Yes. So there are definitely plans for the vehicle to have some type of communication, both visual and audio. I think most of our current development so far has excluded that, although it definitely become important in the future. I think as a baseline, what's critical is to make sure that the current algorithms are safe and have sufficient level of autonomy to be able to operate even without the need to communicate, because you cannot rely on that. But I think once that's established, and definitely important area in the future would be that visual and audio communication.
Thank you.
All right, anyone else in the last 2 minutes here?
I have a quick question. How do you balance like more exploratory R&D versus like everyday engineering iteration?
Yeah, maybe I can answer that real quick, and if you want to add to that. So I would say, so for instance, within Planner, we have a research team, but I should say that in all of the teams, perception, prediction, and planner, there is a research component for sure. And even the research that we do within our team, it's not, you know, something that is going to happen in 6 months or a year or 2 years. It's something that is very closely related to the current algorithmic architecture of Planner and also other teams. And so just because of the fact that there's still open challenges, I think throughout the stack, I would say that, yeah, everything is very tightly integrated.
Mm-hmm.
Yeah, that's very true for perception as well. So we don't have a separate research and a separate execution team. We have the same engineers, they're trying to understand the same problems. Most of what we do ends up being some form of research. We've already sort of like explored what it is that's happening in the current state of the art. And there's a spectrum where like some of this research could be like in a month or 2 months, you figure out the answer. Some of them can take, you know, 6 months maybe until like from prototype to when it's finally on the vehicle.
Great.
And then I'd probably, you know, quickly add on my side. Definitely agree with what was already said. I think the other thing is like, you know, really grounding kind of research in by first understanding like kind of the limitations of our current system, the failure modes, things that we're seeing on the vehicle. That makes it much more clear on like how to resource, you know, more researchy things, because at some point you'll realize that like, this particular class of problem is just not solvable with the direction we're currently going. So we have no choice but to like, you know, resource these, you know, a couple initiatives to solve it. So.
Cool. Well, thank you guys. We're at about time here. So Kai, Marin, and Sarah, thank you guys so much. I know you're very busy, so appreciate you taking your time to chat. Always better for you guys to go over the engineering slides than me, so appreciate that. And then for anybody who really liked what you heard, we have all of our jobs posted online at zoox.com, and I'll end with an hour is just never going to be sufficient. So if you're curious to learn more, our website, they just redid it and it's actually pretty cool. But if you guys have any follow-up questions about anything that was discussed here, universityrelations@zoox.com, you can send it there and we'll get back to you.
Thank you, everyone.